We are discussing objective 1 from H.C. Verma, and magnetic properties of matter is the name of the chapter. So first question is, a paramagnetic material is placed in a magnetic field. Consider the following statements. Statement number 1 is, if the magnetic field is increased, the magnetization will also increase. Yes, the statement is correct. And the second statement is, with increase in temperature, the magnetization is increased. No, the second statement is wrong. With increase in temperature, the random motion of uh, atoms increases and it becomes difficult for aligning those magnetic moments which are now vibrating more randomly and with more energy. So, with increase in temperature, magnetization decreases. So statement A is true and B is false. We are left with option B. In the next question, there is a paramagnetic material which is kept in a magnetic field. The field is increased till the magnetization become constant. If the temperature is now decreased, the magnetization will, we have to give the answers. As it appears that with increase in temperature, with decrease in temperature, Xi should increase, but it is mentioned that saturation has a saturation has achieved, so magnetization has become constant. So we can say after saturation, when the saturation is achieved, Curie law states that if the object is far away from saturation, we can apply Xi is inversely proportional to temperature in Kelvin, but at saturation Xi become constant. So in this question, as saturation is achieved, we can say that Xi will remain same. If a ferromagnetic material is placed in an external magnetic field, the magnetic domain, the magnetic domains which are in the direction of external field will increase in size, but which are opposite to the direction of external magnetic field will decrease in size. So both increase and decrease in size will occur for different domains again, which are in the direction of external magnetic field. Those domains will increase in size, and which are opposite to the direction of external magnetic field will decrease in size. So option C is the correct answer. A long straight wire carries a current I. The magnetizing field intensity H is measured at a point P which is close to the wire. A long cylindrical iron rod is brought close to the wire so that point P is at the center of the rod. The value of H, as H is associated with the external field that depends only on the current, and that will be mu naught I by 2 pi r. R is the distance of point P. H will not change, but due to induction in the magnetic rod, as the rod is made up of iron, a ferromagnetic material, the net magnetic field will increase and induction will also take place. But again, the H is B external by mu naught, and external magnetic field will remain same, so H will remain same. Okay, so option C will be the answer. The next question is, the magnetic susceptibility is negative for, obviously magnetic susceptibility is negative for a diamagnetic material because it is defined as I by H. Susceptibility is defined as I by H, and I and H are opposite in direction in a diamagnetic material. So Xi is negative for a diamagnetic material. In the next question, the desirable properties for making a permanent magnet is high retentivity and high coercivity. Why it is so? A permanent magnet should retain its magnetic properties. Hence, it should have high retentivity and should not be easily demagnetized when an external magnetic field is applied nearby it. So, it should have a high retentivity also. In the next question, an electromagnet material should be made up of soft iron because soft iron has again low retentivity and low coercivity. We don't want it to be remain magnetized when the current is off, and so it should have low retentivity, and also we don't want it to uh, retain some magnetism, and it should not oppose the magnetic field which is produced by the current. So it should get easily demagnetized, or it should have low coercivity. Okay, thank you.